Talks. I'm glad to have you here. So let's get to it, shall we? Howdy. Welcome to another day at Oogie's Tech Talks. I'm here with my wonderful producer and friend Joe, who just said hello. Today we're going to talk about the same thing we talk about every day. But in this case, we're going to talk about two specific parts of it. The packet structure, and because we'll be referring to that later as well. So the packet structure and modulation. So let's deal with the packet structure first. Like any digital communications, Ethernet, wireless Ethernet, it has a packet structure. It needs to know what data is sent when. The data itself is just little digital ones and zeros. 0 volts, 3.2 volts. 3.2 volts is a 1, 0 volts is a 0. So all of your voice data, all of your pictures, all of your messages, those are all digitized and then run out as strings of ones and zeros. Those get put into a modulator and get modulated onto the RF carrier at whatever frequency plan they want. Within reason, obviously, the FCC kind of regulates that, as does the ITU. So, what kind of modulation do they use? First, let's start with what is modulation. You have a wave. It's a voltage that goes up and down a certain number of times a second. So, it has a frequency to it. Now, if you make it go higher in amplitude, and then make it go lower again with those digital ones and zeros, you're doing AM modulation, amplitude modulation. If, on the other hand, you decide you want to change its frequency to slower and then faster, that's frequency modulation. There are all sorts of different modulation types, and there are all sorts of different encoding types as well. In this case, 5G, all of these cell phones, 2G, 3G, 4G, 5G, they all use phase modulation. Now, the phase modulation that they use varies. They can do QPSK, which I'll explain in a minute. They can do 16 QAM. They can go all the way up to 256 QAM. And this is the same regardless of whether they're using 900 megahertz, 1.8 gigahertz, 2.4 gigahertz, the 3.7 to 6 gigahertz band, the 28 to 30 gigahertz band. They still have to modulate the data on there. A sine wave by itself is a car with no passengers. So, to phase modulate something, first you have to know what phase angles it's at. And this can be expressed just by looking at the sine wave as it goes up and down, but it can also be expressed via a vector state diagram. Now in that vector state diagram, you've got 0 degrees, 90 degrees, 180, 270. And the signal stays at the same magnitude, and this is magnitude regardless of where on the phase you're going. It travels like this, because that's all that's really happening. It's just going up and down just like a circle. It's basically describing a circle continuously as far as the phase of it is concerned. So, if we
you're saying that it's a wave or a spiral?
It is a wave.
Not a
But
spiral.
when we're looking at it on a vector diagram, we're just analyzing the phase and the magnitude of it separately. This is a nice analysis tool for figuring out where in phase you are. So at this point in time, we're not putting any data on this thing. So it actually constantly lands here at 0 degrees. Now we're going to modulate this thing. And what we're going to do is we're going to just take one stream of data and we're going to tell it to flip the phase 180 degrees. So when we put that digital 1 in there, right here will do. We've got a digital square wave generator, and we've got our oscillating source. we'll look at a timeline of 0, 1, 1, 0, 1, 0, 0, 1. So this is the data bits that are going to be coming into here. This is the simple oscillator. This is the modulated output. So we've got a 0 in there. We're in phase. The next time slice, we put a 1 in there. That flips the phase 180 degrees, which on here is drawn like that. So that's where our phase is now. Next, we've got another 1, so we stay at 180. Next, we've got a 0, which means we flip back to that first phase, right there. So we went from that phase angle to that phase angle. Now, you don't get a lot of data through like that. That's not really very bandwidth efficient. That's not an efficient way to use that pipe. You could push more data through that pipe if you wanted to. So if you up level a bit and put a second data source in to a second mixer using the same source shifted by minus 90 degrees, take that output and mix it with this output, you get a single output which produces a QPSK signal. BPSK stands for biphase shift keying. It means 2 phase states. QPSK stands for quadrature phase shift keying, 4 phase states. However, what you end up with in this sum is a mix of 2 different signs. So if you mix 0, and since you've already put a minus 90 delay in there, minus 90, what you get out is 45. Which means 0 in there, 0 in there, your first vector is right there at 45. This one doesn't exist anymore. Excuse me for a second. So, if you change this, this is at 0, 0, 0. And we'll call these the I stream and the Q stream, in phase and quadrature. So this one's shifted 90 degrees. It's shifted up 1 quadrant. When you mix these two, you get the difference between them. So if you go to a 1 here on Q, so that is going to be a 0, 1. We're going to shift it right there. Take that guy, make him a 0, make him a 1. Oh, sorry. 0, 1. Because Q by itself had changed down to there, so our new vector is there at 315 degrees. That's a 0 and a 1. It's 2 data streams. You're just changing the vector. What that looks like in the real world, looking at it on an oscilloscope, is that. You've got 4 separate phase states, each 90 degrees separated from each other. That's what you would see if you looked at this on an oscilloscope or just analyzed it in the real world. So the next thing that happens, you'll have, let's see, let's change I to a 1, so that becomes 1, 1, and that is at, let's see, 45, 135, 225. That's where it ends up being. And with an I1 Q0, you are at 135 degrees, that's 45 degrees. So, that's 2 data streams. Put 2 more in there. And in this case, have them control the amplitude of the thing. Now all of a sudden, you start to get into a higher density. Now you've got 4 data streams, all on the same carrier, all on that same pipe. But your vector diagram begins to look that's because your symbol density, and these are all symbols, becomes higher. So now you've got not just phase state steps, you've also got amplitude steps. You're going from this amplitude to this amplitude, which is actually higher, as drawn from 0. The distance to this one is much greater. The distance to this one is much less. The distance to that one is greater. So that's why it's called quadrature amplitude modulation. And 256 QAM means 256 of these spots, 8 data streams. That's how they get the data onto the carrier. And they've got a demodulator, which basically reverses this entire process in the phone as well. Now, on to packet structure. Every piece of data that they send goes into what's called a payload. They define a certain number of bytes worth of data. A byte equals 8 data bits. They've got a certain number of bytes that they can allocate into the payload. Great, so let's say you put 1,000 kilobytes into that payload and you're streaming them through 1 bit at a time. So 1,000 kilobytes is 8,000 kilobits per packet. However, when they get through a router or a switch, sometimes they come in out of order. So you need to put something in there that tells it which packet were you. Because somewhere they've got to strip the data back out and then put it all back in the right order so that you can understand the person you're talking to.
Well, they come out of order because sometimes the signal's been sent to different satellites or different repeaters, and then it has to come back to the source and then regroup.
That's also correct. When you do a handoff, that's one of the things that happens. But what more typically happens is inside the repeaters, the repeater demodulates the data, and then it puts it through basically a Mac chip. I don't know if they use Mac chips specifically, but what these do is they have big FIFO buffers. And so they just basically stuff all this data in, and then when they're ready to burp the data out, they try to burp it all back out, but it may not all come out the same order. But all the packets will come out. What they do to stop this problem at all, and this is the same thing in Ethernet. It's the exact same function in Ethernet, in wireless Ethernet, it's the same function. They put a header on each packet. Now this header contains a lot of things, including the packet number, as well as the IMEI number of the phone, and in 5G, the location of the phone, and a few other things. So the packet header contains a lot of information. If you ever hear somebody talk about metadata, the metadata is the data outside of this payload. The payload contains your conversation, your phone, your text messages, grocery lists, whatever. The header and the footer at the other end contain CRC, cyclic redundancy check, as well as some packet status about the packet itself, and a bunch of other information. These two things are where the metadata lies. And so, that's where you dig if you want to find out where somebody is. Hey, thanks much. Have a great day. Sorry for the little delay there. I was looking at producer Joe, who was pointing off to the wind. Am I supposed to?